Right, so this is our first video on optimization, just introducing the idea. So we're now looking at section 4.3 in the textbook. And these are the so-called max-min problems. So these, like related rates, are word problems, except that um, the objective in these word problems is different. So with a related rates problem, you're trying to get a relationship between two or more rates of change. Here, we are interested in trying to maximize or minimize some quantity. Okay, so the basic strategies for an optimization problem are not any different from those when you're doing related rates, right? The first steps are always the same. You've got to read carefully, and it's always a good idea, where appropriate, to draw a diagram. Right? Determine what the quantities are that you're dealing with, assign variable names to those quantities, figure out which ones are changing, which ones are fixed, and in the case of optimization, you're trying to come up with some quantity that you want to optimize. So you might have something like, maybe you're trying to optimize something like profit or something, right? And so that profit is going to be given in terms of some expression, right? And it might involve several variables. We don't know how many variables are involved, right? This is going to be something that we work out by reading the problem, is how many variables do we need to consider in the problem. Of course, we only know how to do calculus in one variable, and so we have to figure out a way to take this quantity p, and we need to figure out how to write it as a function of a single variable, because we know how to do max-min problems for functions of one variable. And so the way we usually eliminate any variables is we look for constraint equations. We might be doing something like maximizing area with a constraint on perimeter or something like this. So we look for constraints and we use those to eliminate variables. Once we've got it in terms of a function of a single variable, well, then all the techniques of chapter 3 come into the picture, and we know how to solve the problem, right? The rest is just calculus. A couple of technical considerations to keep in mind. Um, you want to pay attention to the so-called applied domain, right? So you're going to be writing down some function. It might involve more than one variable initially. You're going to cut that down to one variable, but you want to pay attention to what values that variable can have. In particular, what we're looking for here is, what's the domain of this function that you're trying to optimize? If you're lucky, the domain is going to be a closed interval, and then we know that for closed intervals you can use the extreme value theorem, right? And once you have the extreme value theorem, we know how to proceed. We know that we find the critical points, we get the corresponding critical values, we calculate the endpoint values, we compare those numbers, and we see which one is biggest. That's going to give us the maximum, or the smallest if we want the minimum. If the domain is not a closed interval, then we got to be a little bit more careful, because we don't have those endpoint considerations. We don't have a guarantee of a max or a min if the domain is not a closed interval, and so we need to do a little bit more care. We're going to be looking for critical points. There we'd want to classify that critical point, right, as a min or a max, and then we'd want to look at that sign diagram and look at other considerations that would tell us that a local minimum is the absolute minimum, right, or that a local maximum is the absolute maximum. So here's a very simple example. We'll just do the setup, right? Maximum area for a rectangle with a given perimeter, right? So we draw a rectangle, right? Doesn't have to be a perfect rectangle. We label two of the sides, x and y. Okay, so we want to maximize the area, right? And so we see that area is a function of two variables, x times y, right? Well, we don't know how to maximize a function of two variables. We only know how to maximize a function of one variable, but we have a constraint. We have a constraint on the perimeter. So what's the perimeter? That's the total length around the outside. That's going to be 2x plus 2y, right? Because two of the sides have length x, two of the sides have length y, and that perimeter needs to be 30, And so from here, I can solve that for, let's say, y, divide everything by 2, subtract x, y equals 15 minus x, right? And so then I can say, well, the area as a function of x is x times 15 minus x. And I can even give a domain in this case, right? What's this? Well, okay, so first of all, x is a length. It can't be less than 0. I mean, really, it can't be equal to 0 either, but including the endpoint is not a bad idea because then we get a closed interval where the extreme value theorem applies. And in any case, when x is 0, the area is 0, and clearly 0 area is not going to be the maximum. So we might as well include that endpoint. What's the maximum possible value? Well, the other extreme, right? X can't be any bigger than half the perimeter, right? Because the perimeter has to be 2x plus 2y. That has to add up to 30. Y also cannot be negative, so the smallest y would be 0, and then I would have 2x equals 30, so x equal to 15. Right? And notice also that the area at the other endpoint is also 0, and so we expect that the maximum is somewhere in between. And how do we find that max? Well, we would take the derivative, set it equal to 0, find our critical points, and go from there. Okay, I'll leave that as an exercise for you guys to try out. We're going to move on to some other examples in the next videos.